Hello everyone. In the last couple of modules, we introduced the three mechanisms for heat transfer. Then we looked at heat conduction, in which we talked about Fourier's law of heat conduction, introduced the idea of thermal conductivity, said that it is a material property and how it is going to vary. So we also looked at couple of example problems, and one important idea about thermal conductivity of gases versus liquid and metals was shown through this table. And as an engineer, we would like to have an idea about the ballpark values of the thermal conductivities of various substances. So, air is about 0.025, water is 0.6, copper 400, aluminum around 200, and stainless steel around 15 to 18 depending on the grade of it. So, with this I would leave this rest of the stuff about what are the how is K, what is K consisting of. There are two parts, one is the lattice part, other the electronic part. So, you can look at that as a theory in the slides. We will go to another very important definition, which is that of thermal diffusivity. It is very important from heat transfer point of view. All of you would have recall from fluid mechanics, you have a quantity mu over rho, okay, which is your viscosity divided by rho, and that is called as nu in fluid mechanics. That has the units of meter squared per second. Thermal diffusivity is a group of terms which is nothing but K over rho Cp as is seen in the slide, and K over rho Cp also ends up having units meter squared per second. It is essentially the ability of a material to conduct heat energy relative to its ability to store thermal energy. So, K represents the conduction aspect, rho Cp is essentially like the mass. Okay. So, the ability of the fluid to mass times specific heat kind of term to store the thermal energy. So, substances or materials which have a large alpha or thermal diffusivity will respond very quickly to changes in the thermal environment, whereas those materials with smaller values of alpha will be more sluggish to reach a new equilibrium condition. This is the takeaway. So, alpha is K over rho Cp is something we need to know, we need to remember that, and what it physically means is the ability to conduct heat divided by its ability to measure of its ability to measure of the ability of a material to conduct heat to the ability of the material to store thermal energy. Okay, and you have a couple of numbers here just for reference. Copper, it is about 117 into 10 to the power minus 6, because K is about 400. For insulating substance like wood, it is 0.0177. For air, it is about 22.5 into 10 to the minus 6, and look at it. So, one is of the order 100, other is of the order tens, and the other one is of the order 0.1 or 0.2. So, couple of orders of magnitude spread is there in the values of thermal diffusivity. Later on, when we come to convective heat transfer, this quantity alpha will play a very important role in deciding whether the fluid is going to be able to transport momentum or transport heat effectively based on the ratio which is called as Prandtl number, which is nothing but nu over alpha. We will come to that in convective heat transfer. Okay. So, with this background, let us go to the most important part of the conduction heat transfer, that is the derivation of three dimensional heat diffusion equation or heat conduction equation. We are going to present it in Cartesian coordinates, and we will also set up the derivation in cylindrical coordinates and leave it as an exercise for all of you to do. We will also introduce the boundary conditions that are typically seen in heat transfer heat conduction problems, and the idea is that different boundary conditions would be needed to solve this differential equation. So, what are they? How are they written mathematically, and from that how the solution for temperature distribution can be computed. So, we are going to start with the heat diffusion or heat conduction equation. So, the idea of this is your objective is to determine the temperature field in a medium resulting from conditions imposed on the boundary. So, the variable, the independent variables in a heat transfer problem would be x, y, z and t. If you are talking of cylindrical coordinates, it would be r, theta, z and time, and spherical coordinates would be r, theta, phi and time. So, 3-dimensional and time, 3-dimensional in space and time, and we want to get temperature field which is T as a function of x, y, z and t. So, we want to find out how T is going to vary, because dt by dy, dt by dx are all those things which are going to be important, which means I need the temperature distribution. Just as in fluid mechanics, we needed the velocity distribution to get the shear stress, here we need the temperature distribution to get the gradient for temperature, which is going to give us the heat transfer rate. So, let us just get on with the derivation. So, we have here control volume, which is dx dy, and this is dz here. So, this is a control volume, this is my coordinate system x, y and z, and if you are looking at the fundamental equation that is of relevance here, that is the energy balance equation. So, I am just drawing the control volume properly, and it is E dot in minus E dot out plus E dot generated is equal to E dot stored. This is the governing, this is the general energy balance equation. Now, if I am able to write expressions for all these 4 quantities, we will be able to get the differential equation. So, let us look at these surfaces given as A, B, C and D here, and let me use a slightly different color for this. E, F, G and H would be the backside faces, and I do not want to clutter the diagram. So, let me just show arrows on this side on this face. This is one set of arrows, the other set I will use a slightly different color. So, this is the second set, this is going upward, q of y plus dy, and if I go back to the third color, which is z, q z, this on this face is q of z plus dz. Come back to my red, which is q of x plus dx. So, this is my control volume here, and I have shown through these arrows how energy is flowing into the control volume and out of the control volume through these 6 control surfaces. The ones in red represent the flow in the x direction, ones in yellow represents the flow in the y direction, and ones in this dark blue represent the flow in the z direction. So, let us look at term each of these term by term. So, we are looking at a homogeneous medium, no bulk motion, that means there is no flow, no bulk motion, and we want to have a infinitesimal control volume, infinitesimal CV of dimensions delta x, delta y, delta z. Let q dot be the volumetric heat generation rate, that means how much energy is generated per unit volume. So, this could be because of a chemical reaction, it could be because of combustion, it could be because of anything. We are looking at volumetric heat generation rate, which is uniform, that is watt per meter cube, and the density density is rho, which is constant, specific heat is Cp, these are all constant values. Okay. So, we want to write now how each of these terms are going to be seen for this particular control volume. So, let us look at these terms one by one. E dot in. So, what does E dot in represent? E dot in represents the energy coming into the control volume from all the directions across the control surface. So, if you look at it, we have this as q of x plus q of y plus q of z. E dot out is nothing but, if I use a different color, E dot out is q of x plus dx plus q of y plus dy plus q of z plus dz. Energy generated is E dot gen, which is nothing but volumetric heat generation rate into dV, which is the volume of the control volume, which is q dot into dx dy dz. So, in this control volume, if this is the volumetric heat generation rate, what is the total energy? The volumetric heat generation rate times the volume of the control volume is the total heat generation rate. And what is the rate of change of energy of the control volume, which is nothing but E dot St, which is mass into specific heat into change in temperature. Mass is fixed, specific heat is fixed. So, it is nothing but rho into volume into Cp into dt by dt. Why is this a partial derivative? This is a partial derivative because t is a function of x, y, z and time. Therefore, this is a partial derivative. So, this is mass into specific heat into rate of change of temperature with respect to time. This is what is giving us the rate of change storage of energy within the control volume. Okay, now, putting these things together, what we are going to do is E dot in minus E dot out plus E dot generated is equal to E dot stored. Let us put these terms together. Q of x plus q of y plus q of z, which is E dot in, minus q of x plus dx plus q of y plus dy plus q of z plus dz plus q dot, which is the volumetric heat generation rate, dx dy dz is equal to rho into dV, which is dx dy dz Cp dt by dt. Now, what is this? In general, we know f of x plus h is equal to f of x plus h times f prime of x. This is the definition of derivative. So, q of x plus dx is nothing but q of x plus dq by dx of x into delta x. F of x plus h is equal to f of x plus this is your h and this is your f dash of x. So, like this I am going to write for everything. So, what I will see is q of y plus dy is nothing but q y plus dq y by dy into dy. Let me erase this so that it is neat. Similarly, q of z plus dz is equal to q z plus dq z by dz into delta z. So, I put these together here. So, let us just make this life a little bit nice. So, I substitute for these and what you will see, the q x's cancel off because of the negative sign and I am left with dqx by dx into delta x plus dqy by dy into delta y plus dqz by dz into delta z. This is the E dot in minus E dot out term plus q dot into dx dy dz is equal to rho into dx dy dz Cp dt by dt as it is. Just for you to retain this flavor, this whole bracket is E dot in minus E dot out. Okay. And we have a minus sign here because this is being subtracted from this. So, minus of this is what is there. Okay. So, now what this is of no use to me because this is a differential equation, agreed, but I have independent variables x, y, z and t. I have a dependent variable which is temperature. I have 3 dependent variables which are q x, q y and q z, which are of no use to me, q z, q y, q x. These should be written in terms of temperature T. Only then is this useful to me. In terms of temperature, if I write, this equation will become useful to me. So, which law or which equation relates the heat transfer rate to the temperature? We have Fourier's law of heat conduction, because this is heat conduction topic. So, Fourier's law of heat conduction is what it is. So, q x is nothing but minus k a dt by dx. And what is this A? Let us go back to our control volume. Q x is in this direction through the area A, B, F, E. So, let me just shade it here. So, I will just shade this area here A, B, F, E, this is the area. This is Q x, which is perpendicular to this surface, which means the area through which the heat transfer is happening is of dimension delta z. Delta z is in this direction times delta y dy in the vertical direction. So, q x is through area dy dz. Similarly, q y is through area dx dz and q z is through the area ABDC, I mean ABCD, which is nothing but dx dy. So, I will put these areas appropriately. So, q x is nothing but minus k into area normal to the x direction, which is dy dz dt by dx and so on. So, my E dot in minus E dot out therefore becomes minus of, what was it written? We had dq x by dx into delta x. Instead of q x, I am going to substitute Fourier's law. So, minus of d by dx of minus k dy dz dt by dx into delta x. This is for the x direction. Then I will write for the y direction is going to be d by dy. I will leave this for you to do, d by dy of k dx dz into dt by dy times delta y, and the third term would be in the z direction d by dz minus k dx dy dt by dz into delta z, which is this bracket, and the other terms involved here are plus q dot dx dy dz is equal to rho Cp dx dy dz into dt by dt. Okay. So, you have a minus sign here and you have a minus sign inside the bracket, and dx dy dz is all common. So, I can bring that out and divide through by dx dy dz. So, dv is not equal to 0. So, dx dy dz is not equal to 0, therefore, I can divide by that throughout and use the, you do algebra, d by dx of k dt by dx plus d by dy of k dt by dy plus d by dz of k dt by dz plus q dot is equal to rho Cp into dt by dt. This is my, I just want to add one little thing here. This is your y direction term and this is my z direction term. So, this is my heat diffusion equation. Let me just go back to the slide and show you what is there. So, this is what we started with, and we have the control volume as shown here, and then we have the equation set up. E dot G is there, E dot ST is there, everything is there, and every step that has been done here has been written out for you, and this is where we landed finally. Okay. So, this is the general form of the heat diffusion equation in Cartesian coordinates, and what kind of an equation it is? It is having 4 independent variables x, y, z and t. So, it is necessarily a partial differential equation, one dependent variable which is temperature. So, partial differential equation in x, y, z and t, you will get, if you are able to solve it, you will get temperature as a function of x, y, z and t. But such equations are very difficult to solve analytically. Okay. Therefore, we need to make several approximations and assumptions to be able to solve this, and that is what we will see one by one. So, if K is constant, thermal conductivity is constant, which is probably one of the most simplifying assumptions, useful assumptions, and it is not wrong, because over a range of temperatures in which you are operating, the thermal conductivity can be approximated to be equal to constant. I am not saying that if the temperature ranges from 100 degrees to 900 degrees centigrade, the thermal conductivity is constant. No, it may be varying in that big range of temperature, but if you are operating between say 100 and 250 degrees centigrade, the thermal conductivity may vary very little, and it is okay to take it as constant within engineering approximations. So, so K being constant is not a wrong approximation. We can use it quite effectively, and that is what is done here. So, let us just go back to our writing board. So, if K is equal to constant, I can pull this out of the differential sign, and what I will get here is nothing but d by dx of dt by dx plus d by dy of dt by dy plus d by dz of dt by dz plus q dot by k plus equal to rho Cp by k dt by dt. And remember, we had this alpha is equal to k over rho Cp. So, this is 1 minus alpha dt by dt, this is q dot by k, and this is del squared t, q dot by k, and this is del squared t. This is your governing equation for constant thermal conductivity. One simplification and you have a nicer looking equation. Nothing has changed except that k has come out of the of the brackets and it is treated as a constant. So, this is Laplacian, del squared is the Laplacian operator, which is nothing but d squared by dx squared plus d squared second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. So, that is the first simplification. The other simplifications are very straightforward. I can have a steady state problem, in which means that nothing is varying with respect to time, which means that dt by dt term is going to go to 0, and that is what you are going to see here as the simplification. When dt by dt goes to 0, we can still retain k as a function of temperature, we can retain k as a function, k as a function of space, and come to this part. So, we have this in the second term, which is this one. This is the one where you have dt by dy, dt by dz and dt by dx, and you do not have t as a function of time. If heat transfer is one dimensional, which is very common approximation, and there is no energy generation and the problem is steady state. So, this is like the best situation for us. What is it? 1D steady state, no heat generation, okay, which means I am going to have d squared t by dx squared plus q dot by k is equal to rho Cp by k dt by dt. Let me write this as d square t by dx squared plus d square t by dy square plus d square t by dz square and dy squared. And what are we saying? We are saying it to be one dimensional. So, let us say 1d in x direction. So, this is 0, these two go to 0, no heat generation. So, this goes to 0, steady state. So, this goes to 0, steady state. So, I am left with d square t by dx squared is equal to 0, which is nothing but partial derivative becomes a regular derivative, which can be solved very easily. Two integrations C1 and t of x is C1 x plus C2, very easy, very straightforward, very nice. Okay. So, now what do you mean by one dimension? It does not mean that heat transfer rate in the other directions are 0. What it means is that the gradients in temperature. So, I will just take a small example. If you are talking of, this is going to be in cylindrical coordinates, but does not matter, you will understand what I am trying to say. If you are looking at a nuclear fuel rod, the length scale is of the order of 3 meters. The fuel pin diameter or the fuel rod diameter is of the order of say 12 millimeter. Okay. So, L over D is like 3000 divided by 12, okay, 3000 millimeter divided by 12. So, it is much greater than 1. Okay. The typical temperature distribution, the values of temperature at R equal to 0 will be of the order say 1200 Kelvin or maybe slightly more. T at R equal to R, this is your R, radius is R, this is your center line. R equal to 0 is the center line and R equal to capital R is surface, may be 300 Kelvin. So, your delta T divided by delta R is like 1200 minus 300 divided by about 6, which is 900 by 6 is approximately 150 degrees C per millimeter. Okay, I am just giving you a ballpark number. Now, if you look at the temperature at Z equal to 0, which is the base, and temperature at Z equal to L, which is the top. So, Z equal to L is this one, Z equal to 0 is this one. You are going to see the difference is of the order of couple of hundred, maybe around 200 or 300 Kelvin. The length is about 3 meters, which is 3000 millimeter. So, this is of the order, let us say 300 Kelvin, it is 0.1 degree C per millimeter. Which one is large, 150 or 0.1? This is much larger. What does it mean? The dt by dr is much larger than dt by dz. Okay, this is z direction, z r here, okay, and theta is this direction. Okay, we are not bothered about theta for now. So, in such a situation, dt by dr is much larger. We can safely assume 1d heat conduction in radial direction, in r direction, is far more important than what is happening in z direction. So, this is what we say as 1d. We are not saying that dt by dz or heat does not flow in the z direction. The heat transport in the z direction is much smaller because the gradients are much smaller in the z direction as opposed to r direction. That is what we mean by 1d. Predominant direction of heat transfer is the x direction. If I said this is 1d in y, then d square t by dy squared would remain, d square t by dz square and x square term would cancel. So, 1d in y would mean d square t by dy square remains. Okay. So, depends on how you choose your coordinate system, is going to be like that. Okay. So, that is what is shown here, and there is one example problem which we will try to solve in the next module. Thank you.